And so with that, I think we'll actually get started. So I'm very excited to introduce our speaker today. She is Sofia Economou. I don't know if I pronounced that correctly, from Virginia Tech. And so she does a lot of very interesting work at the interface between sort of condensed matter theory and quantum information theory. And so we're very excited to hear from her today.
Thank you. Thank you for the introduction, and thanks a lot for the invitation. It's really nice to be here. This is my second in-person talk in the last of almost 2 years. Okay, great. So the title of my talk today is Entangled Photon Factories. And the subtitle of the talk is How to Produce Resource States for Quantum Information Processing. And this is one of the topics. Okay, great. One of the topics that we pursue in my group under kind of a broader umbrella of quantum networks, photonic entanglement, photonic quantum computing. That's the middle topic over here. We're also doing work with matter qubits, quantum control, and looking at matter qubits for quantum computation. I'm not going to talk about that today. And we also work on quantum simulation algorithms, especially variational algorithms. So if anyone is interested in the other two topics, I'll be happy to discuss those in the team later today. Okay, but for this talk, I'll focus on the middle topic, and I'll give quite a bit of introduction, because I'm guessing many people working in quantum information are not particularly familiar with kind of measurement-based models of quantum computing and how quantum networks work. So I'm going to have quite a lengthy intro. So that's what I'm going to start with. Talk about entanglement and measurement in quantum information processing. Then I'll move to a specific class of states called graph states. I'll discuss why these are of interest, which is for quantum computing and quantum communications. And then finally, I'll get to the work from my group, which is how to generate such states. Okay, so for this audience, the slide is probably not needed, but just to start establishing some graphic language. So this talk is going to be, I think I might not have a single equation. Okay, this is technically an equation, but other than that, I just have graphs. So I'll start establishing this language early. Okay, so here I just included one of the 4 Bell states. Of course, the state is entangled. You cannot write it as a tensor product of different products of the different single qubit states. And of course, these are purely quantum correlations. So the language I'll be using, the graphic language, is the following over here. I'm going to be denoting qubits by circles, and I'll be using sometimes different colors. That's not too important. I'll explain when it is. And then lines to denote entanglement. So for now, you can think of this as a Bell pair. It's actually something that's locally equivalent to a Bell state. I'll define this more precisely a few slides down. Okay, so the first primitive I want to introduce about how you can think about entanglement as a resource is what happens if you have 2 Bell pairs. So imagine you have 2 Bell pairs owned by different parties who are far away from each other. So you can imagine the orange qubit is some matter qubit sitting in someone's lab here, and the green qubit is another matter qubit sitting in someone's lab, across the country. And what you want to do is you want to establish entanglement between those 2 parties. So if each of these parties has a Bell pair, and you can imagine these middle qubits here, the purple and the blue, are photons, then they can send the photons down to the same location. And then if you do a Bell measurement between these 2 photons, you collapse those 2 photons in a Bell state. And the impressive thing is that the remaining 2 qubits have now collapsed into a Bell state themselves, even though these 2 qubits have never interacted. So this is kind of a first view of how you can use entanglement as a resource. You can use it to create states that are delocalized in the sense of geographically far away. This was shown has been shown many times. An impressive experiment was this one from Delft, where they showed entanglement over a kilometer away between two matter qubits, in this case MV centers, one in lab A, one in lab B. This is an aerial picture of their campus, and you can see that these are 1.2 kilometers away. And the idea that I showed in the previous slide and that was implemented here is called entanglement swapping, where you make this projective measurement on an entangled basis and you transfer the entanglement out to these remote qubits in A and B. Okay, so here I want to start introducing, okay, I lied, I have some equations. I want to start introducing the Bell measurement mathematically, and the reason I want to do it is to lead to more physical pictures, so bear with me here. Okay, so measurements, we can represent measurements in quantum mechanics as projectors, right? So if I measure in the separable basis, then these are the 4 projectors for 2 qubits. Okay. Okay, I hope that's not something I did. Okay, and then I can define the 4 Bell states, right? They are given in terms of the product states this way. And then I can create projectors. Okay, there's a way to go from one to the other, which is with the Hadamard and the C0. And then I can write down mathematically the projectors onto the Bell states, which mathematically denote the outcomes of the measurements, right? So to get, if my measurement device says I got C+, then I need to apply this projector onto my state. I need to normalize it afterwards. But the important thing here is that I do a C0, then I do a single qubit gate, then I measure on the computational basis, and then I do another set of gates. So the reason I'm showing this is because I would like to start thinking about what happens when I do single qubit measurements in a state that has been already entangled. So I'll get to that in a moment. So Bell state measurement is important, for example, in entanglement swapping that I showed you before. It's also important in teleportation, right? Where you want to teleport to an arbitrary quantum state. It's a single qubit state you don't know. You want to teleport it into the purple qubit, which is somewhere far away. And then you can make a Bell measurement between these 2 qubits, which are in the same location. And following that, you get basically the state you started with up to some Pauli byproduct. Okay, so this is how teleportation works. So this is another example where entanglement is a resource and Bell state measurement is what allows you to use it as a resource. Okay, so let's go back to entanglement swapping. We already saw this. So now let's go back kind of to the mathematical expression, and I want to show you why I bothered showing that to you. So let's take this step by step again. Let's look at entanglement swapping step by step. Again, I start with these 2 Bell pairs, and I do an entangling gate, right? So my measurement is broken down into coherent gates, unitary gates, and projective measurements on the computational basis. So first, let's think that I literally do this in the experiment, right? That's not always what happens. But if this is what I literally did, then I start with C0 gates between these 2 guys. And when I do the C0 gates, what I end up with is a 4 qubit entangled state. So there's this intermediate kind of step, which I might or might not do in the lab, but conceptually, that's what happens, where I have created a higher dimensional entangled states. It's 4 qubits. If I make single qubit measurements on this now, right, following the prescription up here, then I transfer the entanglement between these 2. So I could just start from the middle and ignore the fact that I kind of took this mathematical step from the top to the middle. And I could have started from a 4 qubit entangled state. And then by doing single qubit measurements on the middle qubit, specific single qubit measurements, I have transferred the entanglement to the outer qubits. So now this is an example of how if I have more than 2 qubits, this can also be thought of as a resource, because by single qubit measurements, I can create 2 qubit in this case, or multi-qubit states on qubits that are not directly talking to each other. Okay, so this were just a few motivational slides, hopefully. And now I want to more precisely talk about graph states and define them properly. Okay, so first let's look at the definition, and I'll discuss in a moment why they're interesting. So graph states are quantum states that can be described with a graph. And again, the circles are qubits, the lines denote entanglement. But I want now to get a little bit more specific than that. So I'm going to put, to tell you exactly kind of a constructive description of these states. So every qubit is first put in a state plus, which is just the equal superposition of 0 and 1, or the eigenstate of Pauli X with eigenvalue plus 1. And then anytime there's a line between two qubits, you do a CZ gate between those two qubits. So this is a constructive definition of the state, right? If I give you now, because you know these rules, an arbitrary graph, you can just write down the quantum state. It wouldn't be very pleasant for more than, let's say, 4 qubits, but you can do it based on this definition. Okay, so why do we care about such states? These states became very well known, starting from this seminal paper by Rausendorf and Briegel, which introduced the concept of measurement-based quantum computing. So in there, I'll talk more about this model, but the idea is that if you have a resource state, so here I just drew a 4x4 lattice, but you can imagine this being very big if you want to do an actual computation. What you can do is you can create the entanglement you need up front, and then do quantum computing just by doing single qubit gates. So this is in contrast to the usual circuit-based model that most of us study, where you start with unentangled qubits and you do the entangling gates dynamically as you run your algorithm. So graphs that have a regular structure like this are also called cluster states. Some people in the community use the word cluster and graph interchangeably. I think to avoid confusion, reserving the name cluster state for regular lattices that can be used for quantum computing is probably the most kind of proper thing to do. So that's how I'll be using it. But you can write down an arbitrary graph, and you would call that a graph state. Now there's an alternative definition of a graph state, which is equivalent to what I just showed you, which is the following. For every qubit, you can write down an operator that has an X Pauli on that qubit and a Z Pauli on all the neighbors connected by lines. And the graph state is actually the common eigenstate with eigenvalue 1 of all those commuting operators. And to actually do things with these graphs and compute stuff we want to compute, it's much nicer to have this kind of formalism than have the constructive definition. And the nice thing is that you see that for this state, for this type of definition, all I need is these n commuting operators. So I can, yeah.
So those look a lot like toric code stabilizers. Is there a useful connection to thinking of that way, or no?
There are connections, yes. You can also have, there exists a toric code analog of the cluster state model of quantum computing, where you take the graph in 3 dimensions, and then you can do basically exactly toric code measurements and computation, and you consume the graph state in the 3rd dimension and the 2nd as well simultaneously. Yeah, but there's a lot of connections in the abstract formalism because these are stabilizers. Okay, so the nice thing is that now you only have to keep track of n operators, right? Instead of having to keep track of all the coefficients of the state. Okay, so the stabilizer formalism is very useful for various things. Quantum error correction is one. I just had the slide more for students and people who have not seen these things before. Maybe it's still elementary for this audience, but just to make sure everybody's following. You can see some simple examples that help you build intuition about stabilizers. So a very trivial example is just take a single qubit and find the operator of which that qubit state is an eigenstate. So in this example, the plus state is a eigenstate of X with eigenvalue 1. I can take other sets of commuting operators like XX and ZZ as a tensor product on 2 qubits, and these commute, so they're common stabilizer state is a Bell state of E+. And you can easily check that this works. And other stabilizer states are GHZ states, some quantum error correct encodes, and of course graph and cluster states. And I'm going to now focus on graph and cluster states. So I just want to show you an example because this is probably a very familiar state to many people, the GHZ state. So this is the equal superposition of kind of the most extreme classical states, all up and all down, all zeros, all ones. And this state is locally equivalent to the graph, which has this form, the form of a star with just one qubit removed from the center. Okay, so hopefully this is enough of an introduction of graph states for people who have not seen it before, so we can move on to see how we can use them. Okay, so this is the promised slide on measurement-based quantum computing. So this is a general overview and contrast with a circuit model. So in the circuit model, all the qubits start in a product state. Typically, we initialize them at 0. In the cluster model, we start in this cluster state or regular graph. In the circuit model, we do single and 2 qubit unitary gates as our algorithm tells us. In the cluster model, we do single qubit measurements, which are also dictated by the algorithm, but they're also dictated by the outcome of the previous measurement. And the reason for that is that if you remember in the example of teleportation, when we did the Bell state measurement on the 2 qubits, the state that was teleported was not exactly psi, it was psi up to a Pauli. So this is why we need to have this feed forward, because we basically need to undo that random Pauli that comes out as a consequence of the measurement, right? Because measurements are probabilistic. But this is something we know, and it's a classical, not quantum feed forward, in the sense that you need to adapt measurement basis. It's not an entangling gate you need to do. And then the last step, of course, as you make these measurements, you're disentangling qubits from the graph. So you can think of where you are sort of in your measurement process, column-wise, as being a snapshot in time of the circuit model. So in the very end, you have kind of consumed all the entanglement. You're in the last step where you just have one column left. And that's the analog of being kind of at the very last step where you make your measurement on the qubits in the circuit model. Okay, so I just want to show a little bit of, this is also background, how you would do gates on this. So here I'm introducing some arbitrary state. You can always create that, but let's assume you bring it out from the outside. Otherwise, this graph is defined the exact same way as before. And let's say now I want to do a single qubit gate on psi. What you need to do is you need to make measurements, the appropriate type of measurements on your qubits, so that the rightmost qubit is you, the gate you're after, psi, acting on psi. Okay, so you use the Euler decomposition for that. And you can show that if you measure your qubits in the plane, next to the plane, given by these different angles telling you how far away you are from the x-axis, then you end up with what you want. And you see you have all these byproduct operators, which come from the randomness of the measurement. So you might need to, either undo these or just keep track of them when you finally do your readout. Okay, so this is how you do single qubit gates in the cluster model. This is one way to do a C0. So again, you start from 2 qubits that are in arbitrary states, and you do x measurements on those, y measurements in between, and some x. And then there's nth qubits over here undergo a C0, and otherwise are in this state. So there's many nice review articles by some of the authors of the original paper that discuss more how this model of computing works. Okay, so now thinking about how you implement this experimentally, one interesting thing about it, in addition to the fact that it's a very different model than the model we're used to thinking about in circuit-based quantum computing. And circuit-based, I don't mean superconducting qubits, I mean the circuit model of superconducting quantum computing is that we don't need to generate the whole state at once, which would be a problem because then we would have to somehow have those qubits survive, not either not get absorbed if they're photons or not decohere if they're matter qubits. But we can actually generate several layers and start consuming those, and then generate dynamically at the later layers. So what that means is that the fact that you can do all the entanglement up front and also dynamically is that you can allow for probabilistic gates. And that's important for photons, where 2-qubit gates are not deterministic generically. I'll talk about that more in a moment. Now, another thing is that you need your measurement to be fast enough, right? Since everything is measurement based, and you need the feed forwards to be fast enough. So you need to be able to adapt the measurement basis on the fly as you get measurements on the single photons. So the typical physical systems where this model is pursued is photons. And some of the reasons are the 2-qubit gates there are probabilistic. I'll talk about that in a bit. So the entanglement can then be generated offline. Since this is a probabilistic thing, you can kind of try until you generate the state you want and then use it, which is a very different thing than having to generate it in an algorithm where, if you fail to generate it, then you kind of have to start all over again. And then single qubit measurement is fast compared to at least most matter platforms, and you can do feed forward. I also wanted to mention that recently there has been a paper, this was from, I think, the summer, no, I guess it was January, from PsiQuantum, who kind of are trying to build a quantum computer roughly based on what I told you about, but they have introduced a new model called fusion-based quantum computing, which has many similarities with this model. It also does measurements. They do some of the 2-qubit measurements dynamically, that's one difference. And the resource state here is a GHZ state. So what they need to do their computation is kind of smaller GHZ states of photons rather than this big cluster state. So, from our point of view, if we can generate these resources, either these regular lattices or GHZ states, that could be very impactful for both quantum computing and other things, including quantum networks. So let me just give a little bit of a background on quantum networks, how these states would be useful there before I tell you how we propose to generate. Okay, so perhaps the most kind of well-known version of a quantum network is you have two parties that are separated. This is a simple one-dimensional network, and you want the two of them to establish entanglement. And the problem is that photons are attenuated as they travel in optical fibers, so you can't just create an entangled state and send the photon down all the way from Alice to Bob. So instead, what you do is you chop down the distance that you can split in half and then split that in half, etc. And you can put these two types of intermediate nodes in between. So one node contains memory qubits, which are shown here as lambda systems. And the other type of node is this red node where you do photonic Bell state measurements. And the idea here is that you generate entanglement between the matter qubit and the photon. And at the red node, you do entanglement swapping, just like we discussed in the very early slide. So that means that if I take a right qubit from a blue node and the left qubit of the nodes to its right, then I can establish an entanglement link between them. So whenever these Bell state measurements succeed, again, remember these are probabilistic, then I have established an entanglement between neighboring matter qubits in different nodes. Once all that has succeeded, then I can make a projective measurement between the memory qubits within the node and swap out the entanglements one more time. And at the end, I have measured everything in between, and I have created an entanglement link between Alice and Bob. So there's some challenges with this approach. One is that I need classical information to become transferred between distant nodes. because I need to know whether this Bell state measurement here succeeded or not in order to do the entanglement swapping between the memories. So you need, at this node, you need both this entanglement swapping to succeed, or the Bell state measurement and this Bell state measurement to succeed, and then you would go and do the Bell state measurement here. So the fact, of course, that Bell state measurements are probabilistic limits their rate, but the fact that you also need classical information to be sent back limits the rate additionally, right? Because you're limited now by the speed of light. And you also need, in addition to that, you need to do some kind of entanglement purification. I'm not going to get into that, but that could also limit the rate further. So people are looking at alternative ways where they don't use quantum memories. Also, I should say that you also have pretty heavy requirements on the quantum memory itself, because you need all these memories to remain coherent, all these matter qubits, until all the Bell state, all the entanglement swapping steps have succeeded. Okay, so there's this alternative protocol for quantum networks and quantum repeaters that is all photonic, and it's based on graph states. So a lot of the things I talked about graphs will hopefully be clear here how they're used. So now you still have two types of nodes. In these purple nodes, you generate a photonic graph that has this shape. I'll talk about this more. And then you send half the photons on one side and half on the other. And you have these pink nodes that receive the photons over here. And then you make measurements pairwise, Bell state measurements between the photons that came from different sides. And one thing you can see kind of immediately is that now you have many opportunities for this Bell state measurement to succeed. And there are things that you don't have any memory left over here. There's no qubits left in the primary nodes. So that kind of overcomes in principle some of the issues with the other type of repeater I showed you. And to see why this works, let's look at some additional properties of graph states. So these are more general than the measurement-based quantum computing I showed you before. This holds for any graph. So the first property is what happens if I make a measurement on one qubit on a graph in the z basis. If I do that, what happens is that that particular qubit is disentangled, of course, because that's a projective single qubit measurement. But the remaining structure of the graph does not change up to some Pauli byproduct operator. So that's nice because I can preserve the structure of the graph with z measurements. If I make measurements in the y-axis, then I'm disentangling that qubit, of course, and I'm doing what's called local complementation on the graph. I'm adding a line between neighbors that didn't have a line, and I'm removing line between neighbors that had a line, shown in these two examples over here. Okay, and then the third kind of measurement primitive we need is what happens under neighboring x measurements. Single x measurements are more complicated. I'm not going to attempt to go into those. But neighboring x measurements are actually simple. What happens is you disentangle those two qubits and you create a connection between their neighbors. This looks a lot like entanglement swapping. So this is kind of the motivating example with the 4 qubits I showed early and measuring the 2 middle ones. Hopefully, kind of this rings a bell from how this works. Okay, so with these rules under what happens under Pauli measurements, we can kind of see why this model works. So again, at each node, we generate this photonic state. We don't worry yet about how we generate it. I'm going to worry a lot about it in the last 10 minutes or so of the talk. And as I mentioned, we send half the qubits to one side and half to the other. Okay, so now let's see what happens at the measurement node, right? So the measurement node receives all these qubits. There's two types of qubits. There are the outer qubits in the structure and the core qubits. You see the core qubits are connected to everything else in the core. The outer qubits only have one connection. Okay, so now you receive those photons in this measurement node and you start making Bell state measurement attempts, right? So probabilistically, but statistically, one of them will work if this is a large enough graph. And let's assume this middle one worked. And we don't care what happened to these. It might have not been attempted yet, or it might have not worked. So now that we have this structure, you see we're starting to build this line of entanglement where now the photons that were measured are gone. And I use this XX measurement that I showed you before in some sense, and I have created this line. I still need to get rid of all these other qubits that are hanging around there, because my end goal is to create entanglement that reaches further out from this node. So looking at the rules, the measurement rules we showed before, what we can do is we can make a Z measurement on all the qubits we would like to get rid of, which are all the ones that are neighboring either failed or not yet attempted Bell state measurements. So if I do that, then I end up with this. But I'm still not done, because I still need to get rid of these qubits and extend the entanglement out. So now I'm using the X measurements. So I do these neighboring X measurements here. I measure these qubits in the X bases, and then, let's go back. And then I can get what I want. So the advantage of this scheme is that I have this redundancy in performing the Bell state measurement. And we also don't need to signal back to the nodes, because there's no memory qubits associated with this protocol. So we're not limited by the speed of light in terms of rates of entanglement generation. Now, one subtle point, however, is that for all this to work, all the qubits in the core have to be there. Because if your Bell state measurement succeeds, but the neighbor is lost, then you have effectively cut that connection with the rest of the graph. So what that means is that you need to make sure that these core qubits are not lost, or somehow the information is not lost. And for that reason, we need to redundantly encode, so use some form of error protection in these middle qubits. And the main error mechanism that happens on photons is photon loss. So unlike matter qubits, who probably most of us are used to, where you have some decoherence and decay processes that we usually describe with T1, T2, and T1, in photons, the biggest killer is that photons are just lost, right? And this is a different type of error that you cannot generically protect against with quantum error correcting codes that you're used to from matter qubits. So you need some kind of loss tolerant encoding. So ideally what you would want is to have a whole bunch of photons to encode a logical photon in a way that if some of these photons are lost, you can still transmit the information. So you can define a logical qubit that is given by, again, a graph state, and particularly this so-called tree graph. So you're placing this orange here shown in the middle with all these photons, and all the lines of the middle photon have to kind of emanate from these qubits. And the reason this works is that you can use the stabilizers. So you can use the fact that you know that if you make a measurement, if you have, let's say, one qubit that you use as your node, then X, Z, 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 and three neighbors, you know that that product should equal 1 because it's a stabilizer. So then if you lose one photon, but you have the rest, you can recover what that measurement would have been if that photon was not lost. Okay, of course, you're assuming that there's no other errors, right? If your qubit first decohered and then was lost, that's a problem. You can build some redundancy to protect against that as well. Okay, so this is how you use one example, how the stabilizers are very useful to do error protection. So these are also called indirect measurements because you're actually measuring other photons to deduce the measurement of a photon that's lost. And you can protect, you can tolerate up to 50% loss with this encode. So then the real thing you're trying to generate then is not, the simple unencoded graph I showed you. It's really this object over here, where all the green little dots are photons and all the lines are entangling connection. And if this looks, daunting and you're trying to generate this, right, this reminds you of your graphs. It kind of is, at least at first sight. I'm going to show you in a moment how we propose to generate them in a not so scary way, hopefully. Okay, so that takes me to the last part of the talk. Let's kind of think of how we would generate photonic entanglement, right? So if you remember, when you do a Bell state measurement, there's this entangling gate and then a projective measurement. If I think about it that way, then to do an entangling state measurement and to do a gate is kind of the same, needs the same resources. I need a 2-qubit gate. So if I want to generate this thing with linear optics, I have to pay the same price that I pay when I do a Bell state measurement, which is that photons don't interact with each other, right? So what I can do with photons, I can interfere them, pass them through beam splitters, and then conditional on a measurement outcome on a photon detector, I get or not the state I was after, right? So there's an inherent probabilistic element. Another option is to use quantum emitters, so use matter qubits, where I can make this protocol deterministic in principle. So I'm going to briefly talk about the first, and then I'll narrow down into the second approach, which is what we're interested in. So this is the probabilistic generation. You imagine you have two Bell pairs of photons, which you can generate with some process pretty efficiently, or at least with high fidelity, perhaps not with high rate. And then you can pass the qubits, one photon from each Bell state, through this beam splitter and some linear optics here. And then conditional on this detector firing one qubit, one count, you end up with a state like this. So you took two Bell pairs and you fused them together into this GHZ-like state. And then you can kind of grow your graph that way. You can now take photons from things you generated this way. And there's also a kind of variation of this that gives you growing this cluster in a different direction, the graph. But every time you do this operation, you need to pay the price of a 50% chance of the succeeding, right? Of course, you can reuse pieces that didn't succeed, so this still scales okay. It does not scale exponentially, but still it's a lot of resources that you need. And people have generated, I think this is slightly out of date. This is on the order of 12 photons, right order of magnitude, this way. Alternatively, you can use matter qubits, and the fact that emission process is in principle deterministic. So you can imagine you can couple a matter qubit to a waveguide, cavity or a waveguide, and extract a photon from that matter qubit. And there was a proposal many years ago from Sirac and co-authors on how to do this with a multi-level system in a cavity. So I want to kind of think a little bit more about how I generate photons from emitters. And I want to think about two extremes, right? Perhaps the most obvious way you can do it conceptually is that you generate the state you want on emitters, and then you transduce into photons, right? So this is conceptually obvious, probably really, really hard experimental. Another approach is to have a sequential emission where I use a subset of matter qubits. So you see here 3 instead of 9. And then I use a little bit of the entanglement I create between the matter qubits and a little bit the temporal resource of firing out photons sequentially. So you can think of these two as trading off spatial and time temporal resources. Right? In one case, I need a lot of qubits, so the spatial resource. In the other case, I need to fire out sequentially photons, which is a temporal resource. And in general, the sequential emission is more practical. One is that, of course, you can use photons as they emerge, as I mentioned before, both for computing and for networks. And the other issue is that from a practical point of view, if you look at which are the good photon emitters, they're not really very scalable systems. They're self-assembled quantum dots, color centers in things like silicon vacancy in diamond, etc., where you have basically one emitter and some nuclear spins around as ancillas. So these systems that tend to not be very good for quantum computing are actually good as photon emitters. So then the first model here, oops, I did not intend to do that. The first kind of conceptual model here I'm going to abandon and focus on the second. Okay, so there was this paper a few years after the Sirac et al. Paper, where they discussed how to generate particular classes of photonic graph states from the simple quantum emitter. So here I have a quantum emitter that has some selection rule. I can generate a bell pair by putting it in a superposition of the excited state and letting it emit. And then I can pump this thing again over and over. And every time I get a photon, it comes out in a state that's entangled with the emitter and the photons that were generated before it. And that's how I can get a GHZ state. What was shown in this paper is that if you now allow one more thing, a Hadamard gate on the spin in the ground state, then between pumping and emitting, you can also do this Hadamard. Then this GHZ state actually turns into a cluster state on the photons. And you can always measure away the emitter and disentangling. So you can get a purely photonic state. Now, this is progress, but you're not happy yet because you still need to do something to get a less obvious graph, right? This is just one-dimensional graphs that are not useful for what we talked about. But they're still, interesting to do experimentally. There's been nice experiments by the Gershoni group in Israel on a quantum dot using excitonic states, and more recently by the Walraff group 1 year ago, where they used superconducting qubit and microwave photons and generated one-dimensional graphs or cluster states this way. Okay, so now going beyond 1D, which is kind of where the more interesting applications lie, what we can do is we can do what the previous slide insinuated. We can start using entanglement between emitters and somehow transfer it onto qubits. So we did this many years ago as a theoretical proposal for quantum dots, where we looked at having a line of quantum emitters that can interact in a nearest neighbor way. And we showed kind of how to do gates on these to extract photons in this latter form. More recently, we also looked at a particular implementation that does not require 2 qubit gates between the emitters and uses an always-on interaction. I'm going to skip over this, but just to give you a feel, with only single qubit gates, we estimated you can get hundreds of entangled photons. Of course, the catch here is you have to catch all the photons, so you don't have gaps in your graph. Now we also want to be able to do repeaters, right? These states I showed you that were useful for quantum networks. And what you can do there is you can use an emitter and an ancilla and a gate between them and do the following. So I'm going to just show you this with cartoons instead of equations. So I can do a CZ gate between the two, and then I can pump out the emitter. I can get an arm. I can measure the emitter, and then I can re-entangle it, pump it out, get another arm, repeat this process, and I can get something that now looks a lot like the thing I'm after, this graph state for the repeaters. And the last step is I use the nice properties of measurement of graphs. And if I make a Y measurement on the ancilla, then I can connect the graph exactly the way I want for quantum networks. Of course, as I mentioned before, we need an encoded graph. So now I need to worry about how do I create these inner photonic connections. And you can do this with adding additional qubits to your protocol. So here, if I want to make a tree, that has a certain depth, then I need to have that same number of qubits as auxiliary qubits. But basically, what you can do is you can start creating these photons, and with CZ gates, hook them up to other emitters, and then repeat this process. I'm not going to walk you through this whole thing, but in these two papers, we describe how to do that and get an encoded version of this. Now, once you have these more specific proposals of how you implement these with matter qubits, you can start asking questions like which ones have better performance in a real network, right? Because now we kind of went back and introduced matter qubits in our protocol. So you could argue that all the benefits of using all photonic encoding, to what extent are they still there? So you can compare to matter-based, memory-based quantum repeaters, and we've done that. Oops, sorry. And we've done that in this paper, where we looked at kind of low-level metrics of the qubits, things like how long do the CZ gates between emitters take, how far away are my quantum repeaters, and compared the rate of establishing a bell pair between the two endpoints over the matter qubits per node. And we kind of tracked out the regime where the protocol I just discussed beats the memory-based networks. Okay, so the last few slides, I want to kind of think a little bit more broadly about this problem, right? So far, I showed you a protocol of how to generate one-dimensional cluster states. I showed you how to generate GHZ states, how to generate repeater graphs, and also encoder repeater graphs, right? But this is kind of, up to the brilliance of the student or postdoc that have worked on this, right? To come up with a protocol like that. And nothing guarantees that that's optimal in any way, right? This is something we came up with. We kind of tried things, they worked. So one natural question you can ask is, can we come up with a general recipe that works for any graph? So you give me an arbitrary graph, no matter how complicated it is, and I give you a protocol to do it. And to make this any useful to our experimental colleagues, we would have to somehow guarantee that this is optimal, or at least near optimal in terms of resources. So can we come up with such a thing, such a protocol that uses the minimal number of emitters? So this is what we want to reverse engineer the problem, given an arbitrary graph. What is a way to generate it so that I don't use, I minimize the number of emitters that produce? And in some sense, you could think about this as a circuit compilation problem, but it's very much not, because in a circuit compilation, you have a final state, have an initial state, and everything's generated with quantum gates, right? With unitary gates. Here, we have all these kinds of elements that are not typically present when you do circuit compilation. So one thing is that operations are non-unitary in general, because you can measure emitters and get rid of them from the graph. The Hilbert space dimension is not fixed, because as you generate photons, you increase the size of the Hilbert space. Photons don't interact with each other. So if you were to do circuit compilation, you could just go and add, C0 gates and replace others. But here you're very restricted. And then photons only interact with the emitter once when they generate them. So you can actually model the generation process of a photon with a C0 gate. And that means that any photons you have not generated yet, you can sort of mathematically incorporate them as being qubits in state 0 without, loss of generality, because these kind of factor out of your state. Okay, so we can actually answer these questions and come up with a time reversed process where I started from a target graph state and I work backwards. And the key elements that we use here is the fact that the stabilizer formals I talked about before is very helpful. Also, we are limited to Clifford operations, which allows us to use the Gottesman-Neal theorem. So that makes this procedure very tractable. And then we also use the notion of entanglement entropy to tell us what to do next. And I'll try to convey this here. So our final state is described by a set of stabilizers. Those are the stabilizers for a graph. The initial state is described by another set, a trivial set of stabilizers, because everything is disentangled in the beginning. So one element we use is the fact that you can have a matrix product state description. That was introduced actually in this paper I showed you by Sirac and Kossers. And the bond dimension of this matrix product state representation tells you something about the entanglement entropy. And another very nice thing about stabilizers is that the entanglement entropy of a stabilizer state is efficiently computable. Actually, here I should put a reference. I apologize for that. This is a paper by Plenio and a co-author from, I think, 2005 or 7. It's a reference in our paper. Okay, so then what we want is we want to have a time reversed circuit where we, instead of photon emission, since we're going backward in time, we have photon absorption. And emitters can be measured, right? But in the forward in time sense, but in backward in time, we need a reverse measurement. Okay, and I'll kind of just show you this schematic, and I'm wrapping up soon. So let's imagine that I want to create this graph state as a very simple example. So one thing you'll notice is that now photons qubits are numbered, and that's an important element of our protocol. The numbering of qubits is important. So different numberings will give you different generation protocols. And then you put them in a kind of 1D, in some sense in 1D, but you still keep all the connections. And then you look at something called the height function, which is essentially the entanglement entropy at each side going from right to left. And depending on what that height function, okay, so one thing I should note is that the maximum of that height function tells you how many emitters you need. So you can right away pinpoint how many emitters you need at a minimum. And after that, you have all your qubits. The emitters, because this is your final state, are disentangled. And then you need to work backwards to see how you entangle the emitters to the qubits and end up with a totally disentangled state at the end. And to do that, you kind of walk through the emitters, I'm sorry, the photons backward, or the graph backwards. And you look at the entanglement entropy. And that tells you, do I need to add an emitter over here using a C0 gate, so do this reverse measurement, which would effectively increase the entanglement, or do I just need to absorb a photon? And that gives me which primitive I need to apply. Okay, yes?
So the numbering doesn't change the height, right?
The numbering can change the height. It can. Yeah, it can change it. I'll show you an example. Actually, I think this slide has an example. So in this example, because I'm looking at the way I'm taking, I'm going from 1 to 2. You know, crossing different number of lines, if depending on where 2 is on this graph. So this is the graph that I showed you. You know, this is the type of graph I showed you as a repeater graph a few slides ago, and I showed you one recipe how you can generate it. But there we didn't worry about how the photons were labeled. For an actual implementation, you could worry because the outer photons are measured first. So you might actually experimentally want to generate those first, so you don't have to kind of keep them looping around in optical fibers. So if you impose that to make these, you know, come out first, then sort of not surprisingly, you need more resources to do it, because these photons are very far from each other. So it's not too, maybe at an intuitive level, not too surprising you need more resources. If you kind of do a more natural ordering where I have, you know, neighbors kind of have numbers that are close to each other, then I need 2 emitters. So this is middle one is equivalent to the generation I showed you from a few slides ago. If I care about the order of the photons to be, you know, the outer photons to be generated first, then you see I need from 2 emitters, I need now 6. And for each case, we can also come up with the circuit that generates. And one nice thing about this is that it scales favorably. Both the algorithm, the classical algorithm to figure out what you need to do scales favorably. There's really nice kind of analysis using stabilizers that's kind of under the hood and allows you to do that. But then also the quantum resources scale favorably. So you see here, we just did a bunch of random graphs and we sampled. We had a high edge probability so that, you know, we wouldn't end up with disentangled graphs. And here you can see as a function of the size of the graph in terms of number of photons, how many C0s you need, how many measurements you need. You know, they all scale polynomially and pretty nice. Okay, so that takes me to my conclusion. I gave you hopefully quite a bit of background on measurement-based quantum information processing. I talked about generating photonic resource states from quantum emitters, and at the end showed you kind of a general recipe for doing that. And with that, I want to acknowledge people in my group. Also, I want to highlight Donovan, who was an undergraduate student working with us at the time, and he's here now. He's a PhD student in the group of Shankar Dasarma, doing really great. And he was the first author in the first paper we wrote on the repeater graphs. And then also Bikun Lee, who's also really outstanding student working in the group of Ed Barnes, who did most of the work in this last protocol I showed you. And with that, just thank you for your attention. Yes.
Okay, exactly. Because you need the basis dependent. You can be one basis is highly entangled.
Oh no, it's not basis dependent. It's generation order dependent. Ordering, yes.
So is there a way that I can actually, instead of trying it, is there like a recipe, like a singularity composition, I can do like the easiest one?
If you do that, so the quick answer is no, because that scales pretty bad. You can have heuristics that tell you roughly how to do it. So not kind of surprising. If you put photons reasonably close to each other that are ordered sequentially, that reduces resources. There are lattices, like regular lattices where that's not possible because somehow you have to, if you loop through the lattice, there's going to be cubes are far from each other. And that kind of would have you guess that you need as many photons as on a lattice dimension, which is, correct. But if your goal is to get a particular graph that has a particular shape and you don't care about the ordering, then you can just use these heuristics to kind of guide you. But then to get a precise answer of, this is exactly the minimal number of resources you need the ordering. Yeah, so in this, I think in some sense, these are very extreme examples, right? Because in reality, I probably wouldn't want to generate all the arms first, right? So this is an extreme experimental constraint, I would say, that leads you to have what I think is here, that probably the maximal number of emitters you need, because these are really separated away in the graph. Yeah, but if you know that order, then yes, this is a unique way to reverse engineer it.
So how hard is that problem, and how good are the heuristics? And it sounds like the sort of thing that would be NP hard.
It is NP hard. I think there's some recent papers. We cite one in our paper that has, for some specific graphs, has some results that are better than that. But in general, it is NP hard. Yes, the graph problem itself. Yeah.
I was wondering if there's like sort of whether tree-like graphs and very highly interconnected graphs like this are sort of wildly different in the amount of resources that they need. And like secondary question is, if you start sort of randomly sampling graphs, you usually end up with tree-like things.
Right, I'm not so yeah. So the question is, if you have tree-like graphs versus more connected graphs, how the resources scale. For the trees, everything we've done so far, they scale linearly with the depth of the tree. So it's not too bad. It's actually pretty easy. You don't need additional emitters to get kind of the branching ratio to increase. So that you sort of get for free. You need, as you go in depth, more, but it's still linear. I don't know if you really need. I don't know if what you're saying. I would actually have the opposite intuition. For example, this one is very connected, and you only need 2 emitters. Whereas the same thing, if I made it into a kind of deep tree, I would need whatever that depth is, which would be more than 2. Of course, these are small examples, but based on what I've seen so far, that's what I would think. Yeah, I think in some sense, kind of having some looking at the graph and kind of looking how far away you are, which has this tree sense, right, from kind of the bottom qubits to the top qubits, gives you some sense of how far these are, how many steps you need to take. I think that gives you some intuition for how many emitters you would need.
So the diameter of that graph is not actually large, even though it has a fairly large.
That's right. That's right. And another interesting thing about graph states is that just by looking at them, you can't always guess how many entangling gates you need to create them, right? Because if I just look at it, of course, I have a recipe to create it. Every line tells me I need a CZ gate, but I can do local operations that change one graph to another with a different number of connections. So the GHZ state is one example. I have a middle qubit and it has all these neighbors, right? So it has as many lines as neighbors. But then I can do a single qubit gate and turn that into a fully connected thing, which would again kind of break a little bit your intuition of how many gates do I need to create it. Mm-hmm. Right. So yeah. So for the square lattice, again, you have to number the photons, and if you number them kind of in an intuitive way of kind of zigzagging around or kind of meandering around, then you would get basically what we've done before, which is linear. So I think this is interesting and useful more when you have less regular graphs and maybe that have encoding, which makes them even less regular, and maybe different types of encoding, like in this example where the one inner photons to be encoded and the outer not. Then of course you manage to come up with a recipe, but oftentimes it might not be obvious how you do that, especially if you want to minimize resources. So I think it'll be more useful for those kind of graphs rather than regular. You can, but that's right. It doesn't scale, right? So that's why we, yeah, exactly. It goes back to your question, scaling.
Yeah. I see that Bill has his hand raised on Zoom here.
And this is Bill Phillips.
There you
go. So early on, you told us that one of the requirements of doing the cluster quantum information processing is the measurement had to be fast compared to the decoherence. Now, this feels a lot like the usual thing we would think of in gate computation. The gates better be faster than decoherence. And when you think about doing a deep computation where you have to do error correction, then there are these thresholds. So what I'm wondering is, what about thresholds in this case? Are they similar? Are they better? Does it depend upon the kind of, well, I presume it must depend on the kind of protocols that you use for correcting errors. And you gave us the example of correcting loss. So could you just say a little bit more about that?
Yeah, so one thing to mention is that regarding the coherence, right? If you try to implement this with photonic qubits, then you don't need to generate all the qubits at once, all the photons at once. You just need to generate a few layers from where you're actually doing the computation.
Right. Yeah, so this sounds great.
Yeah. So in that sense, right, you don't need the whole thing to remain coherent and loss tolerant throughout the computation, which is kind of one of the reasons this can in principle work. In terms of kind of thresholds, yes, so the 50% threshold holds for photon loss, right? With the code I showed you. There's more work, a lot more work coming out on this one from PsiQuantum. I think they haven't quite published everything, but I think these a lot of the thresholds putting in more types of errors from just talking to them seem to be favorable. I don't feel I'm an expert on quantum error correction to comment on what's better if I compare to a particular matter qubit platform, right? But this is a little bit of a distinct type of error, and the codes are different. So I don't know if that's addressing your question or. Well,
yeah, but I'm also wondering, loss isn't the only thing that can happen to photons.
It's not.
So what right. about?
You're right. So in the tree encoding, if I go back as an example, here. Here, right, if I only had one branch, right, I can tolerate photon loss. If I have more branches, I can also do a majority vote kind of thing where I can also tolerate some coherent errors. So there are some type of single qubit errors you can also overcome with this type of encoding. So not just photon loss.
Okay.
And you know, from what I know is that this is not necessarily state of the art, because you know you have you know, tens of people working on this in industry, probably having done much better than what's published right now.
Okay, thanks.